I welcome you all for another session on shear force and bending moment diagrams. So we are discussing a topic called as beam. Beam, we have defined it. It is basically a long member having the smaller cross-sectional dimensions subjected to loads which are perpendicular to the axis. Okay, what is the effect of these things? Ultimately, we have to, our study should converge to what is called as the calculation of stresses because of these loads. What stresses, what type of stresses, okay, how much, okay, we ultimately aim to do that. But still a long way to reach that, and we have some preparatory work. Okay, so we have identified and what are the different types of beams, what we intend to study in our course. We are going to study what is called as a cantilever, a simply supported beam, or overhanging beams. These are the three types of beams which we intend to study, and what type of loads our beams are going to be subjected to. So we are going to have what are called as different loads of say point force. We may have uniformly distributed load, or we may have what is called as uniformly varying load, so which is also called as a triangular load. Or we also may have what is called as a moment which may be subjected to. Okay, these are the different loads we are going to have. So these are the different beams as I mentioned. So for these beams, if I take a section, the section again is going to be normal to the axis of the beam. So I cut it. So when I cut and take one portion of the beam, as we all know that portion also must remain in an equilibrium state. Okay, so that portion is not going to remain in an equilibrium state unless the material at the section develops something. So for the equilibrium of that portion of the beam, the material at the section shall develop a force in the case of our beams, and that force we have called it as shear force. Shear force is the force developed by the material at the section of a beam to keep that portion of the beam in an equilibrium state. Similarly, we also have a moment. Why moment is required? Only with the help of force, whatever the material develops, the portion of the beam is not going to remain in equilibrium state, and therefore that also has to develop something else, what we call it as moment. And that moment developed by the material at the section, we call it as bending moment. Okay, why to find out this shear force, bending moment? You may have to have some more patience. You will understand. These are the ones which will induce the stresses in the members. So if you know at any section of the beam, how much is shear force, how much is bending moment, we can easily calculate how much is the stress at any point and what type of stress. Is it tensile stress? Is it compressive stress? Is it shear stress? All that we can find it out. So therefore, we need to know what is called as shear force and what is bending moment at every section. Okay, at different sections. So at different section I need to know. So as I have shown and I shall show you, demonstrate you further. So at a different section, I have different amount of shear force, different amount of bending moment. Or in other words, shear force and bending moment vary along the length of the beam. Okay, now how they are varying? So varying, that means how they are varying we are supposed to find out and represent that variation in the form of diagrams. And those diagrams we call them as shear force diagram. So what is shear force diagram? Shear force diagram represents the variation of shear force along the length of the beam. Okay, so similarly the bending moment diagram, variation of bending moment along the length of the beam. So this diagram, okay, so as you require some sign convention, okay, we are drawing it, okay, sometimes I call it as positive and sometimes I call it as negative. So what shear force is positive, what shear force is negative, okay, I have to have it because, so when I draw it, when I go for drawing, I may have to represent shear force positive or I may have to represent negative shear force, then how to represent it, all that, for that purpose I need to have sign convention for both of these things. There is no universal sign convention, but we are going to, whatever we are going to follow and most of the books follow. Okay, so I shall state you what is the sign convention. Okay, you may have a, as I said, we don't have universal sign convention, and what may happen if someone else follows different sign convention? No worry, absolutely nothing will happen. The values will remain same, the magnitudes. Only our diagram is going to be the mirror image of what we draw. If you follow a different sign convention, the diagram is probably you may not appreciate at this stage because you have not seen shear force diagram. Very soon you will understand what is the meaning of this. If anyone follows a different sign convention, absolutely no problem, and the values of the magnitudes of shear force and the bending moment at different section, they will remain same. Only thing is your diagram will be a mirror image of what would have been a different sign convention. Absolutely no problem. Don't worry. So what is that sign convention? Okay, just to demonstrate, I shall take this example. What is this? This is a cantilever. This cantilever is of length 5 meters. And so I don't call this as a span. Cantilever of span 5 meters. No one will say it, and it is not correct to say also if anybody says it. So what is span? Span is the distance of the beam between the two consecutive supports. So this is one support, and here I don't have a support, therefore there is no support anywhere, and therefore for cantilever we never use the word span. We say a cantilever of length so much. So this is a cantilever of length 5 meters. Okay, so I have shown here only one line. Please do not think that it is like a bar or thread like thing. It is not thread like thing, it has cross-sectional dimensions. For our discussion purpose right now, they are not going to matter, and therefore the beam is being represented only by the axis of the beam, and therefore whatever the lighting you see here, it is only the axis. Please remember, it has cross-sectional dimensions this way and this way. It may be rectangular, circular, triangular, any irregular shape also, no problem. Okay, right now. So what I said, I want to demonstrate you, explain you what is sign convention. So imagine that I am going to take a section here. Say I take a section here. Okay. So when I take a section something like this is where I am going to cut the beam. Cut the beam. So when for my analysis, so when you take a section, whether you take the left hand side portion of the beam or right hand side portion of the beam, the analysis remains same. This is what you have seen in the discussion of bar also. You take a section, left hand side portion or right hand side, and calculate what is the stress, what is the deformation, etc. Everything will remain same. So similarly here also I can take left hand side or right hand side. This is the right hand side portion. So I take a section, this is the right hand side, and say this is the beam. This is the portion of the beam. Okay, this is where you have section. Okay, you have shear force here. This shear force, I call it as Vx, and this is positive. This is my positive shear force. What is the meaning of this? How do you explain it? Take a section, then consider a portion of the beam. If the portion of the beam is towards right, then the upward force is the shear force, positive shear force. And by chance, I don't want to take this, and I want to take the left hand side portion. You have something like this. I shall not take the complete length, and I have cut it here. And this is where, this is the portion of the beam, this portion I am talking. And this is where you have a section. So this, if you take the portion of the beam is towards left side and left side of your section, in that case, this shear force, we call it as positive shear force. So I shall be explaining it again and again. So understand. So you take a section, and for your analysis, for your convenience, you take anything, either right hand side portion or left hand side portion. Suppose I take right hand side portion, then this is my positive shear force. This is my, if I take the left hand side portion, then this is my positive shear force. I hope you understand. And if I merge, take this portion and take this portion, join them together, then there is no section. If I join it together, there is no question of shear force. If you take this add, they merge and they become 0 and the shear force vanishes. I hope you understand. Okay? If you take section like this, this is my positive shear force, this is my positive shear force. Okay? Then, so this is my positive bending moment. If my bending moment is like this, this is my positive bending moment. Similarly, this is my positive bending moment. This is only a sign convention. Okay, why it is required? To draw it, to have consistency. You cannot have for one portion you have a sign convention, different sign convention, and for another portion you have different one, and therefore this is my positive and positive bending moment. This is, and again if you merge this is a clockwise and this is anti-clockwise, they merge together and you will not have. I hope you understand. If I take this and add together, so that means the section is no more valid, and therefore at this section you will not have any load, no shear force, no bending moment unless you cut it. And for example, so I just take, this is identified, what is the shear force and bending moment? There is no shear force, bending moment. That will come only if I take section. If I take section, I shall have it. So these are my positive bending moment. And similarly, if you have a beam, so this is a beam. If it is subjected to bending moment, okay, so this side till this portion. So I have a positive bending moment like this. So this side, it is nothing but this kind of moment. So it is like this bending moment. So because of this bending moment, this portion is going to bend like this. This is also called as positive bending moment. This is nothing but if I take a line, probably you may not appreciate. So a portion beam, something like this. Beam, which is, I am showing the cross section also. Okay, this is the length and it has dimensions. Okay, this is going to bend like this. So this is what is called as convex shape, and this is concave type. Or in other words, okay, this length has decreased and it has become like this. And this length, it has increased and it has become like this. So in the bottom portion I have tensile stresses, and in the top portion I have compression stresses. This is called as positive bending moment. If the same beam, if it is subjected to bending moment like this, then it is going to bend in a different way. This is how it is going to bend. It is the reverse. The bottom portion is subjected to compressive stresses, the top one is subjected to tensile stresses. Anyway, that portion that is going to come in our next discussion, how to calculate stresses, etc. I hope you have understood the sign convention. This is very, very important. Okay, as long as you follow consistent sign convention, no problem. Even if you follow a different sign convention, absolutely no problem. But you should have a consistency. Okay, so you take section, then you take right hand side portion, then whatever the shear force you take, and always you take like that. Okay, if I take right side, my bending moment is positive bending moment is like this. This is how it is. Okay, I hope you understand. Okay, so this sign convention you have understood. Now let me go to what is called as the procedure to draw shear force diagram. SFD. Shear force diagram and BMD, bending moment diagram. Okay, so now copy the problem. That is the first thing what you need to do, which I have not written here. Copy the problem. Okay, something like this. Okay, it may be a cantilever, it may be a simply supported beam, or it may be overhanging beam. Okay, and then show the loads. Then replace the supports by their reactions. Okay, so when I have to replace and when I don't have to replace. If the beam is cantilever, If the beam what you are discussing is cantilever, then no need to find out reactions. No need to find reactions, and still we can draw what is called as the bending moment and the shear force diagram. Okay, if you are dealing cantilever, you don't have to worry about the reactions. But if we are discussing simply supported or overhanging, whatever these two overhanging beams, if we are discussing, if we are trying to draw the bending moment and shear force diagram for this kind of beam, so your first step is find reactions. Find reactions. Okay, how to find reactions? If you have a support of this kind, if you have a support of this kind, you will have only one reaction like this. Okay, sometimes if you have something like this, inclined thing, in that case, you need to draw a perpendicular, and this is how reaction is. The reaction is like this. And if you have a, what is this? Only hinge support, you don't have rollers. In that case, you have a horizontal force, vertical force, and also a horizontal force. The directions of these reactions may vary depending upon your all other loads, but you can assume it this way. And if your assumption is wrong, in that case you will get these values with negative sign. Therefore, it is not a worry. Okay, but if you are dealing with simply supported and overhanging beam, you have to find reactions, and then this procedure, whatever I have indicated here, that will start. So please remember, since I have taken a cantilever to demonstrate, I have not written that point. I don't have to find reactions and still draw what is called as bending moment and shear force diagram. But if your beam, what we are dealing, simply supported or overhanging, the reactions have to be found out first. If your reactions are wrong, I repeat, if your reactions are wrong, the whole thing is wrong. And believe me, this is normally one full question. It is 16 marks or 20 marks. Many times you may have a shear force diagram, draw shear force diagram and bending moment diagram for the beam shown for about 15 to 20 marks, one full question. Therefore, you cannot afford to make very silly mistakes in the calculation of reactions and end up with wrong bending moment and shear force diagram. So therefore, I shall spend again when I take that kind of beam, I shall again tell you how to find out reactions. But you all know we apply equilibrium conditions and find out basically the reactions, which you have done many such problems already, but I shall be repeating it again as and when I take one such problem. Okay, that is the first step. So what beam you are dealing, and therefore reactions are to be found out or not to be found out. For the beam I am demonstrating, so there is no need. Okay, that is the first step. Draw the diagram and decide whether reactions are to be found. Okay, if required, find it out. Then make preparations. What I mean, this diagram. Okay, I just draw here. So wherever support, I just draw one line, and similarly here also, and maybe here also, or in between, wherever loads are changing, wherever. Okay, so this is what I mean by preparation. Okay, make these preparations. So then you draw one horizontal line. Just to get ready, make preparations for what is called as to draw shear force diagram, and this line is supposed to indicate shear force equal to 0. So upwards it is positive shear force, and downwards it is negative shear force. And similarly, I draw one horizontal line to draw what is called as bending moment diagram, and I say that bending moment, this line 0, and upwards positive and below negative. Okay, all this also I stated in the procedure. All this for all problems that has been done. Then only we shall start. Okay, choose reference. What do you mean by reference? Reference is a fixed point. A fixed point in our beam, or it may be outside the beam, doesn't matter. Usually in the portion of the beam we choose one point. Okay, why it is required? So as we all know that we are discussing mom and we are discussing okay, so mom discussion without section is meaningless. We are going to cut the beam and see what is happening there. Okay, when I take a section, so where I am taking a section, that I have to say. So therefore, the section is at a distance of so much from the reference. I hope you understand. And therefore, for that purpose, I have to choose reference. So reference selection is very, very important. Choose reference. Reference. So for cantilever, okay, I am going to follow this fixed rule, which makes my analysis easier. So it is not a must or anything. Okay, whatever I am telling will make my analysis in a simple way. For that purpose, I am telling what is the procedure. Okay, why should I take this? I shall take the other one, something like that. Absolutely no problem. Okay, so cantilever always free end. Always free end shall be chosen as a reference. For cantilever, always free end. That means this is a free end. This is my reference. I am going to cut here, for example. Then this distance, this is what I am going to take it as positive. Okay, I hope you understand. This is my reference. Okay, if this is my reference, if I cut it here, and at what distance I am going to take it. Okay, so in strictly way, this is negative, this is positive. I can choose. This is a reference. Any section here, I can call it as positive. Okay, so for cantilever, always free end. Okay, so why always free end? Because we have not replaced the support by their reactions. If you are ready to find out those reactions and replace those support, that support by all the three components of the reactions, one moment and one horizontal force and one vertical force, and then in that case you can take the other end also as a reference. So as I said, for cantilever we need not find reactions. Then I have no option. I have to choose the free end as the reference. And for other beams, what are the other beams? What I mean by other beam? Either simply supported beam or overhanging beam. It is one end of any one end. One end of beam. One end of beam I shall choose as the reference. Okay, you may not understand immediately what I mean by all this, but keep this in mind. And when I start using it, you will come to know. Okay, I hope it's clear. For the simply supported and overhanging beams, it is any one end, either left hand side end or right hand side end, can be chosen as the reference. Okay, this is what I hope you have understood this. Okay, identify portions of beams for taking section. So ultimately, I am going to take section. Where all I am going to take section. Probably if required you can name it, say A, say this portion B and this is C. So here wherever loads are there, okay, this is one portion, I call it as one portion of B, A, B and then B, C. Then depending upon the load, depending upon whether moment or uniformly distributed load, etc., etc. So you identify at what portion you want to take the section. Okay, that comes by experience and very easily. It is not a difficult thing. As and when we come across the problems, we shall choose that. We shall decide it. Okay, so this also identify the portions of the beams for taking section. Say for example this. So I have two portions, AB and BC. These are the two portions where I am going to take sections. Okay, so imagine a section. Imagine a section. For example, now let me complete these two steps for the problem what I have. Okay, so what is this? For this, So this is this side now. This is my reference. The free end is my reference. Okay, this is the reference. Identify the portions of the beams for taking section. One is AB, the other one is BC. I hope it's clear? AB and BC. Okay, this is what. Imagine a section. Imagine a section. Okay, so where you want to take section, whether you want to take section here or here. So usually this is the free end. Then from free end we go to the other end of the beam. Normally we start, and therefore my first section is between C and B. Between C and B. Between C and B, it is not at C or not at B. We never take section. Between C and B, it is somewhere in between C and B. Please remember, don't take section at B or at C. Don't do it. It is between C and B. When you are talking about B and A, again, don't take section at B or at A. It has to be between B and A. Okay. So now for this, identify portions for taking section. That is one. I am going to take two sections between what? C and B. This is one portion. What I am going to analyze. And what is the other one? The other one is between B and A. This is what I mean by this. Okay, take a section. Imagine a section. So imagine between B and C. Okay, first between C and B, I am taking a section. Imagine a section. Show the distance x from the reference. Okay. And state range of x. That is, for all this, what you need to do is, by drawing free body diagram, what we call it as free body diagram, that you have to draw. Imagine a section. I am going to take a section here. Okay, so I take a section. This is my C, the portion C of the beam, and this is where I have cut it. Imagine the section and draw that. Show the distance x from the reference. This is my x. This is my reference. And this is what is my x. Okay, this distance where you are taking section, this is my section. And where is that section? The section is at a distance x from the reference. Okay, distance x from the reference. Then what? State range of x. So immediately you write down what is the smallest value of x and what is the largest value of x, so that your section is always between C and B. Okay, so what is the smallest value of x? Smallest value of x is 0. That is at C. And what is the largest value of x? That is at B. And what is this distance? This distance, I know that this is 3 meters. Okay, if I take a section here, this is what is my x. So what is the smallest value of x? Smallest value of x is 0, and the largest value of x is 3 meters. 0 and 3 meters. This is what I mean by state range of x. Okay, so now show external forces. So what are the, between this portion, you are taking section here, this is your portion. So what are the forces? I have one force here, and this force which I P1, that is equal to 10 kN. This is the only force I have, external force, what I mean. Along with this, you also show what are called as positive shear force and positive bending moment. Positive. Okay, now this is where you have to be careful. Okay, I have taken section here. I have considered the right hand side portion for the analysis. Okay, so this is where the section is. Then I have a shear force. This shear force I call it as positive. And this is my positive bending moment. So the beam must bend like this. Okay, so therefore this beam, this will take up, and of course this will also go. Okay, as so even if you become, that is, this is how the positive bending moment. Okay, positive bending moment, and I shall call this shear force as V suffix x. V is the notation I use for shear force, and this bending moment I shall call it as M suffix x. So in general they vary mx. So the expressions may have what is called as x term. The term x, that means the bending moment mx, that means it is a function of x. That is how. Okay, so now show external forces with the positive shear force and positive bending moment. That's what I have done. Okay, now find the expressions for shear force and bending moment. Using what? Using equilibrium conditions. The whole thing, this portion is in equilibrium condition. So what are those equilibrium conditions? The resultant force 0, resultant moment equal to 0. Okay, let me take the force. Say I have P1. I shall start with this Vx, which is my positive shear force. Vx positive. Anyway, this is a moment. It will not come in this discussion. Come here. And this is the other force. And this force is in the downward direction. Therefore, it is minus P1. I shall straight away write 10. And no other force. And therefore, this must be 0. Therefore, what is that? Vx is equal to 10 kilonewton. And do you agree that this shear force is positive? Vx is equal to 10 kilonewton. I don't have x. Vx is independent of x. Vx is independent of x. That means in this portion between C and B, shear force is 10 kilonewton at every section. It is not changing. I hope you understand. If you have something into x, the moment immediately you come to know for bending moment. Okay, Vx is 10 kilonewton. So the shear force is constant. You can find, okay, shear force equal to 10 kilonewton constant for CB portion. For CB portion. Let me complete it now. Okay, so at shear force at C, how much? It is 10 kilonewton. Or shear force at B, it is 10 kilonewton. Okay, 10 kilonewton you draw. Okay, it is upwards positive. So I have 10 kilonewton positive. It is upwards. And what is the shear force at B? 10 kilonewton. So how much is the shear force in between any other point? It is 10 kilonewton. And therefore I shall represent it as like this. And I shall write here that it is 10 kilonewton. Though we are not drawing it to scale, but your friend, you should be able to. And 10 kilonewton, you are drawn so much line. If you have to represent any 5 kilonewton, let it be nearly half of it, or at least less than that. Don't draw a line which is greater than this and write it 5 kilonewton. So let it be proportional, but need not to be scaled. Okay, so this is what I mean by shear force diagram for the portion CB. I hope you are clear. It's clear. So now let me go for what is called as bending moment. So how to find out the expression? Again using what is called as equilibrium conditions. I shall start with this mx. I shall first write always this mx. What is the meaning of this? This clockwise moment is positive. I have written mx with positive sign, plus sign. Clockwise moment is positive. So this is where I am taking section. Please remember, I am taking section here only, and I have already a moment at that section, that is mx. Then vx is this, the force here only, and therefore it will not form any moment. Vx is the force at this section. I am taking the moment about this section, therefore it will not form. Okay, now proceed. You have one force. This force shall have moment in what direction? Clockwise. That is same as this mx direction. Therefore, it is plus. First decide direction. Then how much is the force? How much is the moment? Moment is force multiplied by distance. 10 kilonewton is the force. And what is the distance? What is the distance? X is the distance. This sum of this, you have taken all moments. Sum of all the moments equal to 0. So mx plus 10 into x equal to 0. Therefore, what is this? Mx is equal to minus 10x. Very important. the bending moment. Okay, since I have x here, I can say that bending moment is not constant throughout the section, it is varying. Okay, mx varies. Okay, so how is the variation? How is the variation? Okay, so since I have x raised to 1 here, it is linear variation, or what is called as straight line, and mx varies. And what is that? Straight line variation. Straight line variation. The bending moment, when I draw it, it is going to be a straight line. It is a linear variation. So I know that it is a straight line. To draw a straight line, you require 2 points. If you know the bending of if you want to draw a straight line, and if you know the 2 points through which the line passes through, you can just join those two and say that this is a line, straight line, what I require. Okay, how do you get it? So bending moment at C and bending moment at B, I get it. Okay, so to get bending moment at C, what is the value of x? What is the value of x at C? That is 0. Substitute 0. The bending moment at C is 0. Okay, bending moment at B. What is the value of x? What is the value of x? X is equal to 3 meters. This is minus 10 into 3. That is nothing but minus 30. What is the unit? So it is force multiplied by distance. What is the force? Kilonewton. What is the distance? Meters. Minus 30 kilonewton meters. Okay, I can come back here and draw it. Okay, what is the bending moment at C? Bending moment at C. This is C, section C. Bending moment is 0. It is neither positive nor negative, that means it is 0. What is the bending moment at B? Okay, B is this section. Okay, how much? It is negative, therefore it is downwards. Okay, thus I shall write the value. How much? 30. Please remember, I am not writing minus 30 because I have already written this line on the negative side, therefore don't write again minus 30. Okay, so then how is the variation in between? I know that it is a straight line variation. Therefore, join like this. Okay, you may feel it. Some people draw like this, or some you don't draw it. Just understand. Okay, so now this line also is made sometimes. I hope it's clear. So this is what I mean by between C and B. Now I also have to take between B and A. Okay, similarly, quickly I shall go through now between B and A. Okay, what is to be done first? Imagine section and draw what is called as free body diagram. So free body diagram must have the reference. This is your C, and you also have B, and this is your section. And where is the section? The section is at a distance x. Please remember, this is my section now. This section is at a distance x. Okay, so what is the range of x? What is the range of x? The smallest value of x is, please remember, the section should not go beyond B and A. The section should not come here. So therefore the smallest value is 3 meters. And what is the largest value? Largest value is 5 meters. Okay? Your section is somewhere here now. This is your what is called as x. And what is the smallest? This can come up to here. Or this can go up to here. If it goes beyond 5, it is meaningless. So therefore, this is the range, what I mean by this state range of x. Okay, fine. Show external forces. So at C, I have a force what called as 10 kilonewton. Fine. At B, I have another force. It's called as how much? It is 15 kilonewton. Okay. These are the external forces. Now show positive shear force here. So the portion of the beam is right hand side. Therefore, the shear force positive is like this, Vx. Any doubt here? Okay, go back to the sign convention. Take a section Consider a portion of the beam for analysis. If your portion of the beam is to the right side, then the positive shear force is in the upward direction. Okay, so the bending moment, positive bending moment is like this. This is my Vx, this is my Mx. Okay, this is what we have shown. Then find out the expressions for these things using equilibrium conditions. I start with Vx. Okay, upward force. This is moment. Okay, then this 15 kilonewton downwards. Therefore, it is minus 15. Proceed further. It is 10 downwards, minus 10. Okay, then no other force. This is equal to 0. Therefore, Vx is equal to 25 kilonewton. So make a statement. Shear force does not vary between B and A. It doesn't vary. That means it is not 0. It has a constant value of 25 kilonewton. So therefore, come back here. So what is the shear force at B? Shear force at B is 25. So this is your B. So this value is 10. Now you have to add another 15. So therefore, this is your 25 kilonewton. Strictly speaking, whatever you have, this plus 1.5 times this. I don't have space, therefore to draw 1.5, but I draw more than that and write 125. And here also this end, here also 25. And how is the variation? It is constant variation or no variation. Therefore, this is your diagram, what is called as SFD. For this B, this is our shear force diagram. So let me complete quickly. What is Mx? Start with Mx, this expression. Clockwise moment is positive. This will not form any moment because it is with this section. This 15 is say positive. So 15 multiplied by, what is this distance? So I know that from here to here is 3 meters. Here to here is x, here to here is 3. And what is this distance? X minus 3. For 15 into x minus 3. And proceed further, you have 10, again say positive. 10 into x equal to 0. Okay, therefore mx is equal to minus 15 into x minus 3 minus 10x. Okay, you have only x. Here also x raised to 1, here also x raised to 1, or you can simplify it also, no problem. You can simplify or you can keep it as it is and then observe, conclude. So what is your immediate observation? It is a straight line variation. The bending moment variation, it varies, it is not constant. If you don't have x term on the right hand side, it would have been constant. Or we can simplify and explain. Minus 15x plus 45 minus 10x. This is equal to minus 25x plus 45. It is a straight line. Or even if you keep it as it is and then proceed also, absolutely no problem. What is your first observation? Please write. Bending moment between B and A varies according to a straight line. So, varies linearly. It is a straight line variation. Please write that. So, to draw straight line, now we know that we have to draw a straight line. So, 2 points. Which are the 2 points? End points. Bending moment at B and then bending moment at A. So B is your smallest value of x, that is 3. Substitute 3. Okay. So if you substitute here, okay, here. So 3 minus 3, 0. It is minus 10 into 3, that is minus 30. You can check it here also. Minus 25 into 3, minus 75. Minus 75 plus 45. This is nothing but minus 30 kilonewton meter. Okay. So bending moment at A. That is x is equal to 5. X equal to 5. X equal to 5. 5 minus 3 is 2. 2 into minus 50 is minus 30. Minus 30 and minus 30. Minus 50. So minus 80. So you can check it. Minus 25 into 5 is minus 125. Minus 125 plus 45 is minus 80 kilonewton meter. So this is a straight line variation. You have already written it in between. Okay, now let me come back here. So bending moment at B minus 30, yes, minus 30, it is same point. And bending moment at A minus 80, you draw another line. So strictly speaking, 30 and another 30 and 20. Or a reasonably longer line. And right here, what? It is 80 kilonewton meter, fine. So how is the variation in between? It is straight line. And this portion, okay. So this is what you call as BLD. This is what? This is FD. So this is how we draw what is called as shear force and bending moment diagram. Okay, I hope you have understood. Only first problem. You may have few doubts, no problem. Those things will get clear, solidified, and we shall clarify them in our next class. All the best.